Hello, everybody. Welcome back to Mathematical Statistics. It looks like maybe all of you came back, and that's good news, at least for the first week. Good job. Um, we are in review mode, so mathematical statistics is the probability needed to do statistics. So it's not the first probability you learn, but you need probability behind it. In other words, a course in probability is the prerequisite here. So I spent the last class and I'm going to spend today's class kind of reviewing some things from probability, but I'm all over the place because I'm not doing a semester in 2 lectures. So I'm just picking out things that we're going to need to go forward in here. But I promise you, in the next class, we will start the math stat. So in the last video, we talked about random variables, probability density functions, we talked about indicator notation, and cumulative distribution functions. And in today's video, we're going to talk about expectation or expected value and joint probability density functions. So let's get into it. Okay, so first up is the expected value of, now, expected value. We can have an expected value of a random variable. It's going to take values with different probabilities. And if you're waiting for that coin toss or whatever, what do you expect to see? This is the same thing as the expectation for this random variable, or equivalently, the associated distribution. Oops, expectation, which is the same thing as the mean of the random variable or the associated distribution. So I'm just going to start off a little bit informal here and say that expectation is a probability weighted average. It's going to go right in with the abbreviations because I know sometimes I'm running a little slow by doing this live and not with slides. But expectation is a probability weighted average. So let's look at an example for a discrete random variable. So suppose that x is a discrete random variable. We already know one discrete distribution, the Bernoulli distribution, but I want to just do something different to start. So something that's tabulated that takes on values as seen in this super duper great table. So suppose it takes on the values 0, 1, and 2 with respective probabilities 1/2, 1/4, and 1/4. So this is something random, and sometimes when the experiment is performed, sometimes it produces a 0, sometimes a 1, sometimes a 2, mostly a 0, because we've got that probability 1/2 right here. I am going to write the expected value for x as a capital E of x, and I am partial to square brackets. You could use parentheses. Uh, it's fine. Some journals and books and teachers even will not put sort of any brackets or parentheses. I think that's a little hard to read, so I won't be doing that. But I'll be doing this. And if you use your own notation, as long as it has some sense to it, that's fine. So this is defined as the probability weighted average of these values weighted by these probabilities. And you all know how to do this because, you've had classes and a syllabus comes out and they say the first midterm is worth 20% and the second one is worth 30%, or they probably wouldn't say that, but you would know how to compute your score. You would take each grade times the respective percentage, and that's what we're going to do here. So I'm going to take each value, I'm going to start with a 0, and multiply by its respective probability and add them all up. And we get, in this case, 3/4. So I have, 3 numbers up here, and if I actually added them, I would get 3. And if I divided by 3, I would get 1. And so I would get the number that's, in this case, kind of in the middle. But because this random variable favors 0, this comes up more often, the average is being pulled down towards 0. So rather than getting an average of 1, we're getting an average of 3/4. Make sense? Oops. Okay, so let's write this a little more formally for any discrete distribution. So here is a definition for you. Suppose that x is a discrete random variable with PDF, probability density function, or yes, probability mass function, f of x, which is defined in the discrete case to be the probability that x equals x, the expected value of x, or the underlying distribution. So if x had, say, a Bernoulli distribution, we could talk about the expected value of x, and we can also talk about the expected value of the Bernoulli distribution, the same thing. The expected value or expectation or mean, these are all equivalent, of x is going to be denoted and defined as follows. We're going to use a capital E. I'm going to stick with my square brackets, put an X in there. Now that should be a capital X because we're trying to find the expected value of something random that, is a little unpredictable and we want to know what to expect. So that definitely should be a random variable in there. This is going to be the sum of each value, little x, times the probability that x takes on the value, little x. And I need to sum, or we need to sum over all x. So what does all x mean? Our PDFs have domains, like any functions have domains. That's where they're defined, and they're generally defined everywhere. Our PDFs also have supports, and the support of a function is the place where the function is non-zero, i.e. interesting to us. So you want to sum over the support of the distribution, but it doesn't matter if you sum over every possible number because if your distribution or your random variable doesn't take on that number, this probability, this pro this probability here is going to end up being zero in a lot of places. So it's okay to sum over all possible x, but what I purposely did not write, change the size of this eraser, it's massive. Okay, what I purposely did not write was the sum as x goes from minus infinity to infinity, because that looks like you're summing over integers. And just because the random variable is discrete doesn't mean it's necessarily integer valued. So I think it's weird to write that. So I'm not going to do it. But continuing in my definition, just we have a notation for this if we want. This is the same thing as the sum over x of x times the PDF f of x, because that is defined to be this probability over here. So that's what we did in the last example. Let's just do one more discrete example while we're here. The only sort of named distribution that we know already is, suppose that x is Bernoulli. So it has the Bernoulli distribution with some parameter p. Now we know that means that it takes on two values, 0 and 1. It takes on the value 1 with probability p and 0 with probability 1 minus p. The expected value of x is going to be that value 0 times 1 minus p plus the value 1 times p, and that is p. And as a quick, I'm going to go to the table of distributions that you have, because now we know how to define another column here. I'm on the discrete side, and I'm looking at the Bernoulli distribution. Here is the PDF or PMF. Here is the parameter space where the P has to live. And the next column is the mean of the distribution, which is the same thing as the expected value or expectation. And you see the P right there. You will be able to have this table of distributions on all exams for this class. I think you're going to end up knowing all these anyway, because we're going to work with all of these things on these tables so much, but don't worry, you're going to have these tables with you for the midterms and the final. Okay, let me go back to my board here. So we just did an example of we did two examples of an expected value for a discrete random variable. And now I want to define it for a continuous one. And I think that writing this is plenty good for defining the expectation in the discrete case. And I went on to write it like this because we can see the analog for the continuous case. This probability is always 0 for continuous random variables, but we're going to use the continuous PDF in place of that discrete one, and the sum is going to turn into an integral. So let's do it. For a continuous random variable, x, with probability density function f of x, this now does not represent the probability that x equals a particular x because that's always 0 for continuous random variables. Instead, it's a curve under which area represents probability. The expected value or expectation or mean, I'm just kind of being a little lazy to write all three, of x or of the underlying distribution, like we could talk about the expected value of the exponential distribution, is denoted and defined as follows. So we're going to denote it the same way. I'm going to use a capital E square bracket x, but let me back up here. I'm just going to rewrite this with an integral. And instead of summing over all x, I'm going to integrate over all x. So I'm going to write the integral from minus infinity to infinity of x times f of x dx. And if your PDF is 0 in some places or a lot of places, like maybe your PDF only lives on the interval from 1 to 5, that's okay. You could break this up into separate integrals and you'll have 0 for some of them. And no, you don't need to write each of those out, but I'm going to do it one more time here today in an example. So the only continuous distribution we know is the exponential distribution with rate lambda. The PDF there, you'll recall, is f of x equals lambda e to the minus lambda x. And that holds when x is greater than 0 or greater than or equal to 0. That one point doesn't matter. And it's 0 otherwise. So I'm using this indicator notation where I put the interval from 0 to infinity here and an x. And this is a function of x. So when you plug in an x between 0 and infinity, this whole thing is 1. And you're just left with, plugging your x into this part. But if I plug an x in that's, say, negative, then this thing is 0 and the whole thing zeroes out. That's our fun new indicator notation. And let's do the integral to find the expectation. So the expected value of x, which is also the expectation or mean of this distribution, is going to be the integral from minus infinity to infinity of x times the PDF of x and then a dx. I'm going to actually use this indicator in my integral. You don't have to do this. So one thing you might do here is just go straight to, okay, the relevant values are 0 to infinity. I'll put in an x and a lambda e to the minus lambda x dx. And that's exactly how you do it. But to kind of keep working on us getting comfortable with indicators, I am going to write this as the integral from minus infinity to infinity of x times this entire literal PDF. So a lambda e to the minus lambda x and an indicator that says that x goes from 0 to infinity dx. And so as we run over the different x's here, sometimes this indicator is 0 and sometimes it's 1. The indicator is 0 whenever these x's go from minus infinity up to 0. This is the last time, I keep saying that, but really this is the last time I'm going to write out this second integral because I think you get the point. But between minus infinity and 0, we have x times lambda e to the minus lambda x times 0 dx. So in other words, the whole thing is 0. And then on the other part, from 0 to infinity, I have x times lambda e to the minus lambda x times 1, which no, you don't have to write that, dx. So we end up with the integral from 0 to infinity of x lambda e to the minus lambda x dx. So this is an integration by parts kind of thing. I would probably take the lambda out. Actually, I wouldn't do any of these. I have a trick for you coming up, but we don't know that yet. So how would you deal with this integral? You might say that this is like a u and this is a dv, and do integration by parts using the fact that the integral of u dv is u times v minus the integral of v du. This is not something I care about for, this is not math stat. So I'm just going to give you the final answer, but certainly let me know if you can't get this or come by my office hour, we'll work it out. But once you work this out, you will get 1 over lambda. So that is the expected value or expectation or mean for the exponential distribution with rate lambda. And this is exactly what we talked about last time. Remember, some people parameterize the exponential distribution with a rate and some with a mean, and they have an inverse relationship like this. So if you let the mean be lambda, if you said, I'm going to define the PDF to be an exponential with mean lambda, then your rate would turn out to be 1 over lambda. Make sense? Okay, let's go back to the discrete example because I want to talk now about finding the expectation not for a random variable x, but for a function of x. So let me go back to the case, the discrete case where we had 0, 1, and 2 as possible values with respective probabilities 1/2, 1/4, and 1/4. And suppose we want to find, we know the expected value of x, that's 3/4, but if we want to find the expected value of, say, x squared, what would we do? One option is just to treat this as a new random variable. You may not write it out like this, but you can let a new random variable, capital Y, be x squared, and you can write down the distribution for y. So y is going to take on 3 different values. It's going to take on 0 squared, which is 0, 1 squared, which is 1, and 2 squared, which is 4. And it's going to take on the value 0 whenever whenever x was 0. So this is probability 1/2. And we get that y is 1 only when x was 1. And so this is still probability 1/4. And these have to add up to 1. So the probability that y is 4 is the same thing as the probability that x is 2, which is 1/4. So maybe, you know what, I have to do a little aside here um, because the support for the distribution might change, and you might actually have to add some of the original probabilities. What the heck? Keep erasing. So just as a quick aside, leaving my example of expectation, if we have a new distribution, a random variable x, that maybe takes on the value -1, 0, and 1 with these probabilities, I'm going to use the same ones, then if you let y be x squared, this will only take on 2 values now. It will take on the value 0 or +1, because that's what you get from 0 squared or plus or minus 1 squared. So y will take on the value 0 if and only if x was 0, and that happens with probability 1/4, so we get a 1/4 here, but y takes on the value 1 when either x was 1 or -1. Those are disjoint events. I'm going a little bit more into prereqs here, but you get to add probabilities for disjoint events. So the probability that goes here is the rest of the probability, 3/4, or you can think of it as coming from 1/2 plus 1/4. So let me plug that in. 3/4. So I should have done that example to begin with. Um, why don't I just do it? I'm changing my example. So here is the new example. Sorry about that. I'm going to start with this distribution for x, and I want to find the expected value of x squared. So one way to do this is to think of x squared as a new random variable and find the new distribution for y, and then the expected value of x squared is simply the expected value for y. And now we're back to just a plain old random variable, not a function of the random variable. So this is going to be the sum over all little y of y times the probability that y equals little y. And the only relevant values where this is not zero is 0 and 1. So we're going to get 0 times the probability that y was 0, which is 1/4, plus 1 times the probability that y was 1, which is 3/4. And this whole thing is 3/4, which just as a coincidence happens to be the old expectation for the other distribution for x. So I'm starting a new example here. That's a little confusing. I'm starting with a new distribution for x just to make it a little trickier. Then the other example was just coming out too nice for you to be able to see everything that you need to see. So yeah, this is a function of x. We could find the new distribution and work from that. But this turns out to be exactly the same as, you get this one from for y from squaring this one and squaring this -1. And so this is in fact the same thing as, so I'm going to take on the value -1 squared times 1/2 plus 0 squared times 1/4 plus 1 squared times 1/4, and we end up with 3/4. So what we did here was we found the expected value of x squared a little bit differently. We didn't think of x squared as a new random variable with its own distribution. We instead summed over basically x squared by plugging in each possible value of x times its respective probability. What we did was the expected value of x squared turned out to be the same thing as summing over all x squared times the probability that x equals x. This is us putting a function through an expectation. And let's talk about this more generally now with a function like a g of x. And I think, yeah, let's move to the continuous case. So, or I guess it doesn't matter. Let me finish the discrete case. So in general, if you want to find the expected value of like a g of a random variable x, this is going to be your first instinct should be to say, hey, this is a new random variable y, so this is the expected value of y, and this is the sum over all y of little y times the probability that y equals y. But I claim that, and we're going to prove this maybe next time. We're definitely proving this next week. I don't know about the next class, but maybe the one after that. That this is the same thing as the sum over x of g of x times the probability that x equals x. So one more time, the expected value of a function of x, the function of x is the new random variable, and you should be considering its probabilities. But it turns out you don't have to. You can use the original probabilities as long as you put little x's in front in the sum through the function g. We are going to prove this. This is known as the law of the unconscious statistician, which I think is kind of nuts because I don't think anyone does statistics while unconscious. That would be amazing. But I think the idea behind this is computing this like this is something that people kind of do automatically without thinking about, hey, this thing in here is a new random variable with its own distribution. So I will prove that these circles are equal to each other next week. But let's go to the continuous case. We already defined expectation for x for a continuous random variable, but right now we're talking about functions of the continuous random variable. So as another example, suppose x is a continuous random variable, so continuous with PDF f of x, the expected value of a function g of x, that should be capital in there and random, is going to be the integral over all values minus infinity to infinity of g of little x times the PDF for x. Once again, this is a new random variable that you might call y, and it has its own distribution. So this literally would be the expected value of y, which would be the integral minus infinity to infinity of y times its PDF. So I already have an f here, so I'm going to write this as fy of y. So it doesn't look like the same function, so I'm going to throw in a subscript. And maybe I should have done that from the beginning because there's two random variables here. So let me go back up here and make this f sub x of x, and I'm going to put that in over here. So when you see that you have to compute the expected value of a function of x, you could just do this. You could put that function in front of the PDF and integrate or sum over all possible values. But really, that's a new random variable, and it should be this. And we are going to show that these are equal next week. And that's after we have worked on how to transform PDF. So if you have a PDF for one random variable and you look at a function of it, what is the PDF of the other random variable? We need to know the relationship between this and this in order to show that these two lines are equal. Okay, so I think we are on to joint PDFs and marginal PDFs, or PDFs. I'm going to start in the discrete case. I'm going to just jump right in with an example. And this is going to be a probability density function for two or more random variables. Today, we're only going to talk about two. So suppose that x and y, nice and capital, are discrete random variables with a joint PDF. So joint probability density function or probability mass function. I'm going to call this f of x and y. If necessary, to distinguish it from another joint PDF, you might put a subscript on it to say this goes with the random variables x and y, because you could plug anything in, right? You can look at the random variable x, evaluate it at little y. But for today, I think it's going to be good enough to just start with that joint PDF with that notation. This represents the probability that x equals some little x, because these are discrete, and y equals some little y. And the word and in probability is represented by a comma. So we would write this as x equals x, comma, y equals y. That's just a probability thing. Commas mean and. So I might be able to give you a function of two variables. Eventually we will see some, but I'm going to start off with like a tabulated example. So suppose that x takes on the values 0, 1, and 2, and suppose that y takes on the values 2 and 3, and I'm going to stick probabilities in here. So I need to come up with 6 numbers that add up to 1. So how about 0.2, 0.1, 0.1, maybe 0.05. Let's go big on this one. 0.4, and then I'm going to need 0.15 to make them add up to 1, I hope. I'm sure you'll let me know if this doesn't add up to 1. So the entries of this table represent joint probabilities. The probability that x equals 1 and y equals 3, you just have to go to that place in the table, and that is 0.4. And with our PDF notation, this would be an f of 1, 3. We don't really use the PDF notation like that in the discrete case, but I write it so that we can see the analog for the continuous case where we do need to use it because we can't talk about probabilities of equaling particular values. So what if I asked you, what is the probability that x equals 1, and I don't care what y is? In this case, you're going to have to look at the 1 column for x and say to yourself, x is 1 when you get the pair xy being 1, 2 or 1, 3. And those are disjoint events where you get to add the two probabilities. So this is the probability that x equals 1, comma, and y equals 2, plus the probability that x equals 1 and y equals 3. And you would add these two numbers and you get 0.5. So check this out. If I just go back to my table here and I start adding the columns and rows, I'll get 0.25, 0.5, 0.25, and then let's add across the rows. I get 0.4 and 0.6. I can find the probability that, say, x is 1 or 0 or 2 down here in the margin of the table. For this reason, we call these sort of individual probabilities, when we start with joint probabilities, marginal probabilities. So this is a marginal probability. And if we start with a joint PDF, F between some x and y, the marginal PDF for x is gotten by taking that joint PDF and just summing out the y values. So this is, I'm going to denote it by an f sub x of x, and we're going to get it. This is, I am in the discrete case here. By summing over all y, the joint PDF for x and y. That's how you get the marginal PDF for x alone. And similarly, the marginal PDF for y is, I'm going to denote it by an fy of y, and we're going to get it by taking the joint PDF and summing out all the x's. In the discrete case where summing makes sense. So let me know if there's anything I can clear up, but I am going to go on to the continuous case. Let's do it. Suppose, this is actually a definition. I'll write that. Suppose that x and y are continuous random variables. The joint PDF, that's what I'm trying to define here. I'm going to call it f x comma y, or maybe not use those subscripts. So we're going to call it the same thing. So it no longer represents probability because these are continuous, and we have the same issue we had in the last class, right? If you can measure someone with their height with infinite accuracy, the probability the next person is going to be exactly 64 inches tall or whatever is 0. That's just too hard to do. The joint probability that x equals 1 and y equals 3 for continuous random variables is always going to be 0. So in the continuous case, the PDF turned out to be a curve under which area represented probability. And now we've got something two-dimensional. So this is a surface under which volume represents probability. We've got to do some double integrals now. I'm not good at drawing in 3D, but you've got some kind of surface. And if you want to know, so this is like an x-axis and a y-axis. If you want to know the probability you're in some region down here, you need to find the volume under the PDF by doing a double integral. And we can find marginal PDFs. I have an example coming up, but we can find marginal PDFs by integrating out the variable we don't want. So let's go into an example. Suppose that I have x and y continuous with joint PDF f sub xy of x and y, and it's going to be, just for my example, 3/4 x squared y, as long as x is between 0 and 2 and y is between 0 and 1, and it's going to be 0 otherwise. And yes, we can and will use indicators to say this. So how could we do that? We could write the 3/4 x squared y times the indicator that says that x has to be in the interval from 0 to 2 times the indicator that says that y has to be in the interval from 0 to 1, because we want this function to zero out whenever this does not hold. So if x falls outside of this interval, or y falls outside of this interval, that means this indicator is going to be 0, or this is 0, or maybe they're both 0. But when they're both 1, that means that both of those properties are holding, that we're in the right region for both x and y. So this is how we can rewrite this with indicators. Okay, this needs to be non-negative, and it's like a surface under which volume represents probability. And if you integrate over that whole region, it needs to integrate to 1. So the double integral of this is going to be 1. So I'm not going to do that. We're going to do plenty of integrals today. But if I were to integrate, I can do this in either order, dy dx or dx dy. So if I were to integrate 3/4 x squared y, maybe dy dx, and my x goes from 0 to 2 and my y goes from 0 to 1, I had better get 1, or this is a failed example. Let's talk about the marginal distributions. So the marginal PDF, I'm going to use the same notation, f sub x of x. We're going to integrate over the whole world, minus infinity to infinity, the joint PDF. We're going to integrate out over y. So first I'm going to do this without indicators. What you would do here is you would plug in the PDF. Oops, forgot my integral. 3/4 x squared y dy, and then the integral would be over the y region, which was 0 to 1, because the integrand here is 0 otherwise. And we get, I'm going to pull out the 3/4, going to pull out the x squared. We get the integral from 0 to 1 of y dy, and that's y squared over 2. And when you plug in the limits, you're going to end up with 3/4 x squared times 1/2, so 3/8 x squared. Now, this is supposed to be the marginal PDF for x, but you're not finished. This is not a complete answer. You need to give the values the support for this distribution. Our x's ran between 0 and 2 here, so this is for x between 0 and 2. The ending answer here is going to be that we get 3/8 x squared for x between 0 and 2, and we get 0 otherwise. So don't forget this on the homework problem or something. If I'm asking you for a PDF, either a marginal or some PDF from some transformation, you're not finished if you haven't given the support for the distribution. I'm going to try this marginal again, but with indicator notation. The marginal PDF for x is supposed to be the integral minus infinity to infinity of the joint PDF, and we're going to integrate out y. And I'm going to plug in literally the entire PDF, indicators and all. This is 3/4 x squared y, an indicator that says that x is between 0 and 2, and that y is between 0 and 1. And then we're going to integrate out the y. So the first thing I'm going to do is pull out all the constants with respect to y. I can take out the 3/4, I could take out the x squared, and in fact, this indicator does not depend on y. So I can pull out that entire function, the indicator, on the interval from 0 to 2 of x. And I'm left with the integral minus infinity to infinity of y times an indicator that says that y is between 0 and 1. So this is going to cut off the limits of integration. I promise to stop doing this, right? I'm not going to write this as what I could do is say the integral from minus infinity up to 0 of y times 0, which goes away because it's 0. And then the integral from 0 to 1 of y times 1. And then the integral from 1 to infinity of y times 0, which goes away. But I think you get the point. The indicator is going to define the limits of integration that we should be using. So this is not equals. This is times the integral from 0 to 1 of y dy. And when you do that integral, you get 1/2. And so putting this all together, I'm going to multiply the 1/2 in over here. I get 3/8 x squared, and I have an indicator already built in. So I don't have to remember to go back and give the right support for the marginal PDF for x. If you don't do it, you don't do it. I'll accept your answers on the homework and exams without indicators, but it's really going to be helpful to start getting used to them for reasons. Okay, this is a marginal PDF for x, starting with a joint PDF. And of course, we can find the marginal PDF for y in the same way. I'm just going to write it down. Marginal PDF for y using the same example. I'm going to denote it by an f sub y of y, and it is going to be the integral minus infinity to infinity of the joint PDF. And we're going to integrate out the x this time. I think this is going to be 2 times y, and then an indicator saying that y is between 0 and 1. But we started with a joint PDF, back up here, like this, or like this, and we wrote it as 3/8 x squared times this as the marginal PDF for x, and then we got 2y times this. And so I know you know what's coming here that you've seen in your prereq probability course. We have independence of these random variables. So this is a definition, be the last thing I can fit today. Random variables, whether discrete or continuous, x and y are independent. It's supposed to be yellow. Independent if the joint PDF for x and y factors into the marginal PDF for x times the marginal PDF for y. And that is what happened here, because if you take this times this, you do get back this. And so we got the x squared part going to the x PDF and the y part going to the y PDF, and of course the indicators going their own way. But the 3/4 broke up into a 3/8 times a 2. And so while these are independent, I have a big question for you, and that is, did we really need to compute these marginal PDFs in order to establish independence here, if that was the question? If I'd given you this joint PDF and said, show that x and y are independent, you could find the two marginal PDFs and you can say, oh, look, the product is the original joint PDF, so I'm done. But could you maybe look at the original joint PDF and say, you know, this factors into an x part and a y part. Let someone else sort out the constants. You know, is it 3/4 x squared and then y, or the other way, or something completely different, like 3/8 and or whatever it was. So we can break up the 3/4 in many ways, but can't someone else sort that out? So my question to you is, do we really need to find the marginals, or is it enough to just say it factors? And here I'm out of time, so fortunately I'm going to finish a little bit of review next time, and then we're going to start the math stat. But the answer is yes, if you use indicators. So this is the first reason out of many that I want you to get used to indicators, because we can show that random variables are independent if the joint PDF factors into an X part and a Y part, including the indicators. I'll give you an example of when that fails and what's going on with the indicators there, but I'm out of time. So have a great weekend, and I will see you next time on Mathematical Statistics. Bye.